right, welcome everyone. My name's Sam Jacobs, this is Michael Barkin, and we're with the company Barcom, and we're going to be going over the Enoch processor today. And these are the talking points we're going to be starting with. First, we'll go over, introduce our processor, then we'll talk about the baseline specifications, customer requirements, followed by instruction formats, and then we're going to go over what enhancements we made to those original customer requirements, and then end with a Q&A and closing session.
Alright, so we chose the name Enoch because we were looking at a list of powerful names, and we wanted a powerful name for our powerful processor. So when we're designing our processor, we had two goals. We wanted it to be adaptable to enhancements, as well as, while we did that, still prioritize our customers' needs because they were first. So in sake of adaptability, we made what we call our processor modification toolset, which is a toolset for adding enhancements so that when the customer in the future, as processors get more and more powerful and more gets available, they can enhance their processor even more. So how it works is there's a default state for all of the control words, and then in the cells you can override those default states, and at the end you can generate your entire list of control words inside the CU64.
And to talk further on that, if we look over the past 10, 20 years on how the instruction sets for processors have grown, they started out with, what, in the 90s with 100, 200 instructions, and now they're up to having upwards of 1,000 instructions. And those designing operating systems and for these hardware, it takes a lot of effort to keep up with that, and sometimes they don't utilize the hardware to its fullest potential, and thus we try to keep our architecture open source and adaptable to those needs. And Mike will further explain the next part, how we get our tool set into the actual hardware description language.
So what it actually does is when it's done, you can copy the entire code for the CU64, and this is an example of the control words that it generates. Where the cells were blank, it's put in the default values, and where we have populated the cells, it replaces the default values with our custom values. One thing that makes it really easy to enhance our processor is when you want to add new control words, all you have to do is make a new column in the tool set and only populate the new instructions or the enhanced instructions that require the new control word, and all your old states will be populated with the default, which should, if you design it correctly, do nothing.
And can we go back to the code? And one thing that we decided on with our variable naming conventions is that we decided to go for a very verbose name so we know exactly where they are. Because if you remember our previous assignment 301, when you're not familiar with the hardware language or new customers coming onto our tool set, it can be quite confusing. And unless you have an actual drawing in front of you, looking at the code is not going to really tell you what it's doing. So we went with describing exactly what everything's doing and including an N, lowercase n, in front of everything to describe an active low signal.
So the purpose of that is when, in the future, when new programmers enhance our processor, they can jump right in and they don't have to necessarily look at a list of tables to understand what each of our variables is.
And we took this kind of inspiration, if you look at ARM, how they become one of the most successful IP distributors and designers in the world. Almost all systems out there have used ARM, so we kind of took from their success to inspire how we designed our architecture.
Yes.
Next, we'll go for our baseline specifications from Robert W. Allison.
So these were the baseline specifications that were given to us for our CPU. And this is a big overview. We're going to go into more detailed diagrams. This is how we implemented it.
I can kind of talk a little bit about this too. So here's the execution unit. We took out the control the combo logic for the control unit, just because it just controls all the wires. Starting with the execution unit, it encapsulates the floating point data path, the integer data path, and our BIU. And then down here is where our memory and I/O interfaces are. As you can see, in our IDP, to implement our flags, we had to implement a lot more MUX, and with each new MUX came new control signals, some intermediate registers, came increment enables, decrement enables, load enables. So we'll go further deep down into that as we go.
Okay, so first, this is the default integer data path, and this is our implementation. We added an extra MUX into the R input to enable faster loading of the program counter, because in all of our program counter relative jumps, we felt that it was too slow and we wanted to make our processor faster. So that's how we implemented that. As Sam said, we added extra MUXes for our flags to decide when to take some of our flags from the ALU versus from an immediate value somewhere else.
So this wire here, this bus, this is a 5-bit bus, has an interrupt enable flag, and along with the CNZ, V, and Z, which is carry, negative, overflow, and 0 from our ALU. That goes out here to a flags module that we're going to explain later. We implemented an entire module for our flags. And these MUXes here allowed us in our control words to either take the ALU status or take in flags from either memory, when we had to store them, or from our flags module. And this 64-bit comparator here is tied to ground, 64 bits of ground, along with our entire 64-bit immediate Y value that we use for loading immediate values. And that one's a comparator to ground, and if they are equal, it inputs 0 into here. That way we can actually check immediate values being put in, whether or not there's 0. Also, to check the negative immediate values, we just we chop off the highest MSB of that immediate value, and then we put this in our N flag MUX, which either takes in the ALUN or that immediate value I was talking about into our flags. Now you can't overflow on immediate loading, and you can't get a carry on either, but you definitely can get 0 or negative. So we're going to go further on to the next.
So this is our floating point module. It is, as implemented, basically identical to the baseline. And here are our
these are opcodes,
yeah, our opcodes, or our instruction formats. So in our enhancements, we added new fields. There's an S bit, which is for suppression of flags, so you can, we'll go over it later, but it's conditional setting of flags.
And execution of instructions, too.
We have, the C is for choosing conditional execution of instructions, and the Fs, as of now, are unimplemented. There's still more room to improve, but in the future, one could implement the Fs to do, after a value gets out of the ALU, to do an additional ALU operation on the value before storing it back into the register.
We could also do like a shift or a func field too.
So there's the remaining 3 instruction formats.
Now let's talk. Can you talk about why the PC rel does not have a suppression, the S bit?
Okay, yeah. So one thing about the PC relative, neither sets the flags, and it's almost always conditional anyways, or there are PC relative that are conditional, so it's unnecessary and impossible to use the conditional execution of instruction or conditional setting of flag. So when there is a PC relative instruction, the hardware that handles that ignores it because it's impossible to use our enhancements on a PC relative instruction. So that goes into our enhancements. As I said, we have conditional setting of flags. So this is our flags module that we implemented. There are 4 inputs coming into the flags module, which select from various sources. And then on each actual register, there's a write enable. So how it works is, in our decode state, we check the flag suppression bit. And one design choice that we made here was that instead of checking also for PC relative instruction there, none of our PC relative instructions set the flags anyways. So we decided not to check there because it'd be a waste of hardware. No matter what, it will never change the flags on a piece of relative instruction. That's why in our D code we don't check for it. And in all our other states, the flags write enable register remains the same, so that you have a write enable bit that is only changed when the IR is decoded.
To go over our hardware a little bit, this is the wire I was talking about coming out of our IDP. It is a 5-bit wire which has the carry, negative, 0, overflow, and interrupt and enable bits. And what they do is they feed into 5 separate muxes along with 5 1-bit registers that have the write enable signal right here. And what that's able to do is when we have the S bit, if we pick write enable, when that's low, they're not going to write anyway. So thus, with one control signal, we can turn off all of our updating of flags, so it just gets the previous value. And then we have the ability to either set the flags by loading VCC, clear them with ground, and then take either flags from memory or our ALU flags. And that's all done with 2-bit concatenations of 5 different values right here.
Okay. So our next enhancement, as I was talking about, is conditional execution of instructions. So on your left, you can see a table of all of the suffixes to your instructions when you write assembly, as well as the conditions that are required to meet those conditional values. On the right, you can see our implementation. So in the decode state, if a conditional value is not met, so if we want to, for example, add if there was a carry, if there was not a carry, then it actually skips the execution altogether, therefore saving you 1 or more clock cycles.
And that's something very important too that we'll go on to later. We did some performance testing of the programs that were given from the requirements, and we can show how being able to do the conditional execution has improved performance and taken some time. And then Mike will go over what this graph here means.
All right, so our baseline instruction set has about 94 instructions. With all of our enhancements, we subtracted out the number of PC relative instructions because those don't count, and we calculated between our extra conditional instructions and whether or not setting the flags. There's an additional 2052 instructions available to the programmer and to the compiler.
To build upon that too, that with these many new added instructions, the tool set we have is very necessary to allow the customer to actually feasibly be able to take full advantage of our hardware and implement these in the programs they design.
So if our compiler were to compile for our system, for legacy code, you can compile to the old way, which is just to always have setting of flags and no conditional execution of instructions. However, we went through program 12, which was the program where you jump over a lot of halts. And we went through it and we switched all the logic so that instead of jumping over halts, we have conditional halts. And this could be like a compiler compiling the same exact program for our enhanced processor. And here's an example of the code. So now instead of load immediate, it actually generates a load immediate with setting of flags, or higher setting of flags, a halt if positive, halt if equal, halt if not equal, etc. And here's the continued code that we have. And what this actually does for us, like I said, when the program is actually ran, it goes to fetch, executes previous instruction, and then once it reaches fetch again, it skips the instruction without getting to execute. So our execution block for what that was a halt, was entirely skipped, thus saving 1 clock cycle. But what actually happens when using our enhanced compiler, or a compiler for our enhanced instruction set, is that your program is much more efficient. So for program 12, it may not be a normal program because it is a lot of jumps. This is an improvement that you'll be seeing in every single program that you compile. But in this specific program, we had 25% less space by your compiled code, and actually 6% faster performance.
But to go through it too, a lot of programs don't. All programs are done by getting data, iterating over data, making conditional execution upon that data. So if statements, else statements, case statements, looping. That's pretty much all of our tools for programming. So, I mean, every loop statement has a check. You know, a loop control variable that's checked whether or not to be false or true or within bounds of something. So this does tie into when you get down and dirty into the assembly from this. You're going to notice an improvement pretty much in any programming language you have.
So did you do an analysis on any of the ones that do looping, like the other modules besides 12? 12 just kind of jumps around testing the flags.
No, we did not.
Well, we did do 12 first because it kind of really showed, you know, just a straight down jumping over halts. But definitely in the future, if the customer requires it, we definitely love to go into that and deliver some deliverables regarding that and show, you know, an in-depth analysis whether or not it really does improve performance in that much. That'll kind of tie into kind of our future enhancements. Right, and that leads into Q&A session right now.
Just had a question too.
You like?
Sorry, I just had one and I'm trying to remember it right now. But I was wondering, how exactly did... Never mind, I just realized you answered that question earlier in the presentation. So I apologize for that.
Well, go ahead and ask it. We can maybe elaborate a little further.
Okay.
If it didn't make much.
I was wondering where exactly you checked for the conditional variables, but you said that was in the D code.
Yeah.
Okay, so actually, we do check it, and we do use it in the D code, but it's actually implemented in hardware. So let me go back to that slide and show you.
Okay.
So it's implemented in hardware in the CU64. That combinational logic on the top right is always being used. It's just some gates and some wires.
Okay.
So that's always being checked. However, it's only being used in our decode state.
Okay.
This is a very deep, tertiary superior statement. So.
Any more questions?
Yes.
Earlier, in the very beginning, you had a chart showing the different columns, and you had the kind of baseline instructions, and then places to override those instructions. Are those other columns like different user modes, and in a different mode you override baseline instructions, or are they just added instructions? I wasn't.
Okay, so I'll go back to our program to show you. I think I understand your question. So it's actually you modify the instruction itself. So what you write is a load immediate. So in our example, we have a halt if positive. That's actually within the instruction. Use the bits within the instruction. So it's not a different mode. It's actually a different instruction altogether.
So like a halt, it just puts almost everything to zero, the default state, and does nothing, right? When we have a halt of positive, we got to check in the decode state whether or not our flag bits from our flags module do indicate that the previous instruction did produce that. So if we're expanding upon each of these, basically you take the 96 instructions that we were given, and you multiply that by a factor of how many different combinations of conditional qualifiers there are, and that's where we produce the large quantity of instructions that we have. Thus, the tool helps us be able to just go through and change one column, and then iterate that down over all the subsequent instructions of the same nature.
Is that what you're talking about?
Partially, yeah. But I was curious how exactly you are setting the flags on the loads, but I'm taking a second look at it now, and I think I understand your code more.
So yeah, on the loads, the flags aren't actually, as Sam said, they're not actually taken from the ALU.
Can we go to the
yeah, there's additional comparators so that we wouldn't have to go through the ALU and add additional muxes into the ALU, because we may want to use the ALU for something else while still loading something in.
Okay.
Because if we were to pipeline this in the future, it's the MIPS. During one time, it's taking the PC and adding 4 to it, utilizing the ALU, which is empty during that cycle. But say we want to do something at the same time with our processor in the future.
Okay.
We couldn't really do that if we were just taking the ALU and using it so much during every instruction for this.
The flags module was inside of what other module?
It was right outside the CPU. I mean, it was inside
It's
the CPU.
inside the CPU.
But separate from the IDP.
It's next to the IDP, and they're interconnected within the CPU.
and it takes a 5-bit bus.
One more time, it's within what module?
The
Like
CPU.
CPU?
Yes, sir.
Okay.
Any other questions?
Great job. Thank you. That's good. Thank you.